Hello students, this is lesson U5A03A, where I will be deriving the similarity proportion of overlapping right triangles. Okay, so this situation comes up all the time in different scenarios, in physics and chemistry, in a lot of physical science, so which is why it needs to be brought up in high school geometry. So suppose I have this situation, and I'm just going to focus on just this diagram right here. I have essentially is three overlapping right triangles. I don't know if you can see this or justify it, okay? Pause the video and really observe this if you don't see it. So what I have here is on the left, okay, I have a small right triangle. On the right, I have a larger right triangle, and then I have one giant right triangle overall, right? So essentially I have three right triangles, which is what I have here. I want you to pause the video for a moment, and I want you to label the three triangles with the corresponding letters A through D on all three triangles. Make sure that you get this correct. Mark up also all the angles with the correct number of tick marks. Notice here I have only two tick marks here. I have one tick mark and I have two tick marks there. All right. See if you can do that. Pause video. Hopefully you guys had some time to think about this. Well, and to analyze this a little bit. So what can be said is, okay, all three triangles are going to be the same. And because these two angles here, which I don't know, I have no idea what these angles are, right? So let's call this I don't know, N. Well, actually, let's not use N. Let's use P. And this angle here, let's use Q, right? So let's just think about this. And I have no idea what these things are. Let's call this, I don't know, let's call it S or something, right? So imagine this with me, okay? S plus P plus 90 should equal to what now? S plus P plus 90 should equal to 180, right? Angle S, therefore, should equal to 90 minus P, right? So this guy here is 90 minus P. Okay, so wait, if this angle is 90 minus P, and what's the measure of this overall angle? That's 90, right? So in other words, 90 will equal to 90, I'm sorry, right, 90 will equal to 90 minus P plus, and I have no idea what this guy is, right? So let's call that T. So plus T. Notice now I have 90s on both sides. T will therefore equal to P. Right? Do you see that? T is actually equal to P. So this angle here is actually equal to P. And if that angle there is equal to P, and S is equal to 90 minus P, but wait a minute. P plus Q, what does P plus Q add up to? P plus Q also should add up to 90, right? So if P plus Q adds up to 90, P plus Q adds up to 90, then therefore we can say, oh, wait a minute, P therefore is equal to 90 minus Q. If I take this and make that substitution, what will S turn out to be? S will turn out to equal to Q. So in other words, this angle over here should also equal Q. Or in other words, all of these angles, okay, are deserving of the same tick marks. This angle over here is deserving of two tick marks because that's really angle Q, and this angle is deserving of one tick mark because that's angle P. So anyway, why am I going through this? Because it will help us to identify how to label the triangles a little more efficiently. So if I have one tick mark here, one tick mark will be over there. Two tick marks here, two tick marks will be over here. So all of these, okay, that's what I'm going to do. I am going to label all the triangles with the correct number of tick marks. And then from there, I have a little easier time in labeling things correctly, right? So I can see here that the triangles can be labeled in this manner. I have ABD, then DBC, and finally ADC. Pause the video to see if you can verify this. So hopefully you guys had some time to think about this and that the triangles that you have correspond with what I have labeled here. What we're going to do now is we're going to try to come up with some patterns or maybe some kinds of proportions that we can make up, that we can set up, because all three triangles, as you can see here, are going to be similar based on angle-angle theorem. So according to the angle-angle theorem, because all three triangles are similar, we can then set up proportions based on the sides. So all three triangles, ADB, DBC, and ADC, are going to be similar. For some reason, the triangle symbol is not coming out there, but that's what it was supposed to be. So the altitude to the hypotenuse of a right triangle divides a triangle into two triangles that are similar to the original triangle and to each other. That's a mouthful, but just understand this, right? That if you have a right triangle, if you draw an altitude like such from the right angle to the hypotenuse, what's going to happen is these two triangles here on the left and on the right will be similar to the overall. That's what that is saying. Alright, so what we can do, because all three triangles are similar, we can then create ratios based on the corresponding sides. So what I'm going to do is I'm going to compare the shorter leg to shorter leg between these two triangles, and then do it again for these two triangles. So I have AB divided by DB, that's this guy right here. They should be proportional to DB divided by AD, which is this guy right here, right? And I can do this again for finding the proportion between the ratios of corresponding hypotenuse. So I want to take AD and divide it by DC, and that should be equal to DC divided by AC. And lastly, I can compare the longer leg, right? The ratio of the corresponding longer leg. So I can say DB over BC is equal to BC over CD or DC. So these are the proportions that I can set up. I don't expect you to memorize this. No. Because this is just a lot of information to digest. The main takeaway is this paragraph here. Let me use a highlighter. The main takeaway is this paragraph here. If you can remember, or not remember, but understand that if you have a right triangle and you draw the altitude from the right angle to the opposite, to the hypotenuse, what you will form are three similar triangles, which is this guy here. And once you can make that connection, and once you have that understanding, then you can recreate those proportions that I've circled there in red, which is a major difference between memorizing. So there's a lot of formulas in math, but a lot of times you have to understand it is an illusion. Like math teachers, they come across like knowing a ton of formulas, but really they only memorize maybe a couple of things that help them along the way of recreating that story. Okay, that's what this is. This is a story, and these are the ratios that I'm able to create. Okay, so then there are also other proportions that we can set up. We can set up a ratio between the longer leg to the shorter leg within the triangle. Okay, so I can take so I can then set up the proportion AB to DB is to DB to BC. I can also set up another proportion between the hypotenuse to the shorter leg, and similarly the ratio of the hypotenuse to the longer leg. So these triangles, we can always form these proportions And do I expect you to memorize these again? No, because these three proportions stem directly, once again, from what I've highlighted there. Okay. There is one thing that I do want you to, quote-unquote, memorize, and that is, because there are so many proportions that we can form, is there a single proportion that is, and I have it in bold here, useful, that we can take away from this experience? There is absolutely something that is useful that comes up all the time, as I've mentioned in the beginning of this lesson, because it comes up all the time across math, across physics and chemistry, and all different fields like STEM related, right? And that is, if you have a right triangle and you draw an altitude from the right angle down to the hypotenuse, the very act of doing that partitions the hypotenuse into two segments, which I'm going to call L and M. As it turns out, okay, based on the proportions that we set up a moment ago, we can then conclude that L over N is equal to N over M. And this right here leads us to this equation. So in other words, the partition of the hypotenuse formed by the altitude, that partition, the parts of that hypotenuse, if I take L multiplied by M, I will end up with the altitude of that triangle squared. There's a name for this. The name of this situation is L squared. This should say not R, but this should say N. My apologies for that. Okay, so the geometric mean of L and M is square root of LM, or N is the geometric mean of LM. So N here is the geometric mean. And you're probably wondering to yourself, like, why is this called a geometric mean? Well, this is actually very, very similar to an arithmetic mean. What is an arithmetic mean? You've been using this ever since probably grade school. Okay, an arithmetic mean is you're adding up all the different values together and then you're dividing by the number of values you have, right? Which you end up with something like this. So if I add up all the different values in a given like data set or something, we divide by the number of data points that we have. Here in this case, okay, we are, instead of adding the data points, we're going to multiply the data points together and then take the nth root, which will look something like this. So a geometric mean, because we only have two points here. We only have two values, L and M. L and M is equal to N squared. If we were to take the geometric mean of, let's say, PQ and R, then it would be PQ and R is equal to N cubed, and so forth. And then we would have to take the N cubed, the cube root of those products together. But anyway, that's left for another discussion on the usefulness or the applications of geometric mean versus arithmetic mean. Save that for another lesson in another course, actually. But anyway, the main takeaway, okay, for this lesson is what I have there highlighted in green, which we are going to apply in the next lesson.